Welcome back to the wonderful world of ethers. Today we're going to be talking about those most amazing of ethers called epoxides. These are the compounds, the ether-containing compounds that undergo the most synthetically useful reactions. So we're going to first review reactions of how you make epoxides, and then we'll talk about ring opening reactions of epoxides, and that will pretty much wrap up ethers. All right. So just to refresh your memory, what's an epoxide? An epoxide is a three-membered ring that contains an oxygen. You can hear lots of other terms for these like oxirane, or this particular one is called ethylene oxide. I just really want you to call it an epoxide for the most part. These obviously are pretty strained, right? Remember, when you take an sp3 hybridized carbon or oxygen and you compress that bond into 60-degree bond angle, that creates a lot of strain in the molecule. It wants to pop open like a mouse trap, and so we're going to pop it open with various nucleophiles, as you'll see in a moment. Four-membered rings are pretty strained, but they're a lot more difficult to make, so we're not going to worry about those for too much. And then, strangely, I guess maybe, is that 5- and 6-membered ring epoxides are extremely stable. These are practically inert. So we're not going to worry about reactions of these. In fact, as I mentioned previously, these are used as solvents because they're so unreactive for the most part. Okay, so let's focus on epoxides in this video. Okay, how do we make epoxides? Well, as all of you remember, when you take an alkene and you treat it with a per acid, MCP Ba is one per acid. You can have various R groups here. The oxygen gets transferred to the alkene in a syn fashion to give a syn epoxide, as you see here. So that's one way to make epoxides that we're already familiar with. Okay, three-membered ring ether. What's another way to make an epoxide? Well, previously we talked about when you have an alkene, right, and you react with bromine and water, you can get this compound. It's called a bromohydrin, right? But one thing that I neglected to mention before is that alcohols are pretty decent nucleophiles, especially if you deprotonate them, and alkyl halides are pretty good electrophiles. So lo and behold, we have a nucleophile and an electrophile in the same molecule, and this oxygen is really close to this partially positively charged carbon. So even though there's a lot of strain in forming these epoxides, because of the close proximity of the oxygen to the carbon, it can just kind of fold over and push off the bromine, and that's exactly what's going to happen. So if we look at what we can do with bromohydrins, it's relatively straightforward. We take these compounds, we treat them with sodium hydroxide, and what we get is an epoxide. This might seem a little strange, right? Because sodium hydroxide is also a good nucleophile. You might expect that to just undergo SN2 reaction with the bromide, right? But acid-base reactions happen much faster than any other kind of reactions. So initially what happens is we have this oxygen-hydrogen bond. Hydroxide is a strong base, so the first thing that's going to happen is an acid-base reaction to deprotonate our alcohol. And so what we'll end up with first is this alkoxide, right? Now we have a really strong nucleophile, which is really close to this electrophilic carbon, and it can just kind of move over here. It's going to attack from the top, right? This is an SN2 reaction. We're going to see inversion of stereochemistry here. We kick off the bromide, so the oxygen attack the top face. So again, we're going to get this inversion of stereochemistry. The bond is down here, it's up here. This is your typical SN2 kind of pathway. This is called an intramolecular reaction, right? Because all of this is happening in the same molecule. The displacement, the nucleophile and the electrophile are in the same molecule. Okay, so what can we do with epoxides? We know two ways to make epoxides. What can we do with them? Well, I said these things are like mouse traps, right? They want to pop open. And so if you take a good nucleophile like sodium hydroxide, it's going to pop this thing open. How does this work? Well, I think it's pretty straightforward here. You have your strained epoxide, right? Oxygens are partially negative. These two carbons are both partially positive. So either one could get attacked by the hydroxide, pop it open, and then we have a source of protons here to protonate that O- that we initially generate. So for example, the hydroxide could pop it open here. This is a great reaction because we've relieved ring strain, right? So now we have an O-, and this OH came from the hydroxide. So this is our new bond that formed. This used to be a bond in the epoxide, but that broke. But notice this bond is still there, right? So that O is not gone. It's still attached to the molecule. And now water is a source of protons. So we have a quick acid-base reaction, which gives us this OH group. So this OH came from our nucleophile. This one came from protonating the oxygen in a second step. So I want you to think about this kind of like as an SN2 reaction, right? This is a good nucleophile. It's a strong base. So it's going to attack at the same time that the leaving group leaves. Okay. So why, the rhetorical question that I'm asking here, why do epoxides react when other ethers are unreactive? Well, the reason is because epoxides are really strained. So they're much higher in energy than other ethers, like THF, for example, would be all the way down here. It's not strained. It's happy. So look at the activation energy barrier. It takes a tremendous amount of energy to open THF, whereas it would take much less energy to overcome this activation energy barrier in an alkoxide. And in fact, for THF, look, it's an endothermic reaction, whereas for an epoxide, it's an exothermic reaction. So one is thermodynamically favorable, the other one is thermodynamically unfavorable. Okay, so a much prettier version of what I drew on the previous slide, right? This, again, think about this as an SN2 reaction, right? The hydroxide is ring opening the epoxide. It doesn't matter in this case which carbon we choose to ring open at. We get the same product in either case. Okay, so what kinds of good nucleophiles can we use to do these kinds of reactions? Well, alkoxides could be used. Cyanide is a good nucleophile. Thiolate is a good nucleophile. Grignard reagents are great nucleophiles, so those we can use to ring open epoxides. But notice, we can't mix that together with water. We have to add that in a second step. Lithium aluminum hydride, you want to think about as an H- ion. So that's just going to add an H to one of the two carbons. So you need to make a list of these. These are the nucleophiles that you want to think about as really strong, good nucleophiles that are going to open an epoxide in an SN2-like kind of reaction. Okay, what if we have a choice? What if we have different substitution on our epoxide, right? Here we have a tertiary carbon versus a primary carbon. Well, remember, if we're thinking about this as an SN2-like reaction, the nucleophile is going to prefer to go to the less hindered carbon. So whatever our nucleophile is, if we go back to the previous slide, right, each one of these nucleophiles is a strong, good nucleophile that's going to prefer the less hindered carbon, right? So each one of those nucleophiles in this particular case is going to attack the less hindered carbon. This is called regioselectivity, when you have two different carbons that could get attacked, which would give different products. So the nucleophile in these kinds of reactions is always going to go to the less hindered carbon. So, and because this is an SN2-like reaction, right, the nucleophile is going to attack on the opposite side of the leaving group. So we're going to get inversion of stereochemistry here. The nucleophile is going to be bonded to the underneath side. If the original bond to oxygen was up, the new bond is going to be down because we're going to kick out that leaving group from the opposite side. You're going to see inversion of configuration from these epoxide openings. Okay, so what happens if we want to use a poor nucleophile? Well, think about this as an SN1 kind of reaction. This is not an SN1 reaction, but it's like an SN1 reaction. When we have H plus in brackets here, you want to think about some source of protons with a non-nucleophilic counterion, probably in almost all cases, that's going to be sulfuric acid. Sulfuric acid is a source of protons, but that the conjugate base of sulfuric acid is not going to do anything else in the reaction, so you can think about it as just protons. Okay? So if we take an acid and water, we get the same product that we got from sodium hydroxide. If we take acid and an alcohol, we have a new ether, kind of a product, with the alcohol bonded to one of the two carbons in the epoxide. So how's this happening? Well, it should be pretty straightforward here. So if we think about sulfuric acid as a source of protons, right, we have a basic oxygen that has two lone pairs of electrons. So sulfuric acid is supplying protons, right? So we're going to protonate that oxygen. And what we did, right, is we took a bad leaving group, turned it into a good leaving group. So with a good nucleophile, like in the previous slides that I was showing, you don't need to make this into any better of a leaving group. But with a crappy nucleophile like water, now we need a good leaving group in order to make this happen, right? So now water, which is a crappy nucleophile, can attack the carbon and open this thing up because now we have a good nucleophile. So now our product is going to look like this. We need to lose a proton, which we can do by bringing in another molecule, another water molecule that can pull off a hydrogen and an acid base, or proton transfer step that gets us here. So we have a proton transfer at the beginning. We have a nucleophilic attack here, and then a final proton transfer at the end. This is only going to be a reasonable pathway for poor nucleophiles. It's mostly going to be water and alcohols, much like the SN1 reaction that we talked about previously. Okay, so what about regioselectivity in this particular reaction? This can be a little bit tricky, right? So let's go back to this example that we had previously. We have a tertiary carbon, we have a primary carbon. With sodium hydroxide, right, this is an SN2-like reaction, so the hydroxide is going to attack the less hindered carbon. It's going to ring open here. So we're going to get, actually, so that we can tell the difference here, let's do sodium methoxide, right? So now our product in methanol is going to be, right, the methoxide attacked the less hindered carbon. But let's say that we treat this with sulfuric acid in methanol. Now we're going to get a different product. We've switched the regioselectivity. Why is that? Well, now it's because the methanol actually attacks the more hindered carbon. And this might seem a little bit strange, but we can understand this based on this picture that I have down here, right? So if we go back and we just concentrate on this reaction, right, we have a source of protons. So we're going to protonate the oxygen. And this is the species that's actually undergoing nucleophilic attack, right? And so this oxygen is positively charged, and as we stretch this bond or this bond, we can start sharing more of that positive charge with these carbons. Well, this carbon's tertiary. Tertiary carbons can accommodate more positive charge, so this bond stretches out more, and our tertiary carbon develops more positive charge, so that attracts the methanol molecule to it more. So now this can attack at the same time that this leaves, and we get our product. After we lose a proton, we get the product that I drew earlier. So all you really need to know is that under acidic conditions, you're going to get attack at the more hindered carbon. Under basic conditions, you're going to get attack, or you're going to get nucleophilic attack at the less hindered carbon. Okay, what's interesting about this, and the reason why I call it SN1-like, is because even with these SN1-like reactions, you're still going to get inversion of stereochemistry, and that's because we protonate the oxygen, turn it into a good leaving group, and this attacks at the same time that the leaving group leaves, which pushes the methyl group up, and we end up with our nucleophile, and we end up inverting the configuration of the epoxide that we started with. Okay, so let's do some practice, at least just with regioselectivity. So this, in order to do this, you're going to have to think about strong nucleophiles, weak nucleophiles, like we talked about in the previous semester. So SH minus, it's negatively charged, it's polarizable. This is a good nucleophile. It's under basic conditions. That means it's going to attack the more hindered carbon. So the product is going to be this one. Sulfuric acid, ethanol, these are acidic conditions. This is a crappy nucleophile. So we're going to get nucleophilic attack at the more hindered or more substituted carbon, and this should be ethyl, not methyl. Here we have lithium aluminum hydride. These are basic conditions. The H minus, you can think about it that way, is going to attack the less hindered carbon. We're going to break this bond. This oxygen will get protonated by water. So you have an OH here, and we just have a methyl there, right? Because we added a hydrogen. You could draw in that hydrogen if you wanted to. You could draw this like this or like this. These are the same compound. Okay, so to summarize, there aren't a lot of useful reactions of ethers, and the only one I'm going to really focus on are those reactions, ring opening reactions of epoxides. We can pop these things open like a mousetrap, and the way that we can pop them open is with really good nucleophiles by an SN2 kind of mechanism, or we can pop them open with poor nucleophiles by activating them a little bit, turning them into better leaving groups with acid.